Okay, good morning, Physics 30s. I want to go through chapter 15. I apologize if this might be a little long, but I'll try and keep it as brief as I can because there's just a lot of history and principles. The math isn't too bad, as you'll see. So, chapter 15 covers the history of the structure of the atom, and I've included this graphic right at the beginning because it's a great summary of all you need to know. You need to be familiar with the progression of the model and how, with subsequent discoveries by different physicists and scientists, the model kept changing. So we start with John Dalton, basically early 1800s, and he went under the premise that atoms cannot be divided any further. In fact, atomos is the Greek word for indivisible, which is it's an ironic root for an atom because we've obviously learned that atoms are made up of smaller particles since then. Uh, but we're going to go through the contributions of J.J. Thomson, which you might be familiar with in chemistry, his cathode ray tube and his plum pudding or raisin bun model, if you will. Some of those are, see if I can get this to open up here. So yeah, sometimes we call this the raisin bun model. You'll see that in the notes. Ernest Rutherford's contributions basically found that there was a nucleus in an atom and it was incredibly positive and dense. Most texts that I've come across don't call it the nuclear model, although that's a really good one. They call this the planetary model because it mimics a planet with moons orbiting it. Actually, in this graphic, I kind of like the planetary model for Bohr's version because most moons orbit in the same plane. But for a lot of what I've seen, this is just called the Bohr model, named after Niels Bohr, okay, with the electrons orbiting in specific or discrete orbitals. And then, of course, the last one is the quantum model, which is the reigning model today. And we'll look at that a little bit. So, but in a nutshell, that's the whole chapter. And I just want to show you some of the contributions that each of them made and define them a little bit. And when you get time, these, I know it, hopefully you can read that when you're reading it through, but the positives and negatives here are actually quite accurate in terms of, I'll try and highlight those as we go through because it talks about the limits of each model. You know, the improvements of each model are positive, and then the little negatives here are things that were still wrong with the model until we finally get to the quantum model, which is the accepted model for the time being. And we have lots of evidence to suggest that it addresses all the elements. So we can explain all the elements using the quantum model, which we can't do with all the other models. Anyway, so let's start with J.J. Thomson. He developed the cathode ray tube. There's a nice picture of him. And the tube he was using, shows it in this picture, was a Crookes tube. One of the technical problems was getting it to be a perfect vacuum. If there's air in there, like firing electrons through it would disrupt your results and make it really hard to get anything accurate. So how did he do it? Well, he developed this cathode ray tube, or CRT. And basically, I'll just show you fast how it works. You have a hot filament here that's projecting electrons, and then they're accelerated between those two green plates. And what Thomson was able to confirm right away is that these particles coming off, well, he couldn't see them, of course, but he could see what they would do to a phosphor coating that was on this screen here. So basically, all of this in here was lined with phosphor. And when the electron would hit it, it would excite it and would give off a bit of light. And so that way he knew where it was hitting. And he found really easily that if he applied parallel plates with one negative and the other positive, as you can see right here, then the path would be deflected. So what you see in blue is the path if only these blue plates right here, so there's the positive, there's the negative, those blue plates, the electrons would be repelled by the negative and attracted to the positive, and they would make that path through the cathode ray tube. Very easy to do was also bring in a magnetic field, which you can see here represented by these circles with X's in them. Okay, so this is showing that the magnetic field is into the page. Okay, so I know I'm even in the video, this is probably backwards, but your left hand, you would use your third hand rule. Your thumb would point in the direction the electrons are moving, and your fingers would point into the page. I'm kind of doing it towards you in the screen. That means your palm pushes down. Okay, and so, and that's what happened. These, at least under this configuration, the electrons would be pushed downwards, and then you see there'd be a path with only the magnetic field. Okay, so Thomson was able to confirm, first of all, that the electrons were negatively charged because they moved in the direction a negatively charged particle would move. And so, but he basically found actually three really significant things using his apparatus, and you just need to know the math behind these. So the first one here is he found that when he made the electric field and the magnetic field equal in their strength, okay? So what that would mean is if the electrons right in here, the force from the electric field is trying to push it up, but the force from the magnetic field is trying to push it down. Okay, we can ignore gravity in this case. Essentially, it's inconsequential. But if you could get those balanced, then the easy evidence with that, of course, is that the path would just be undeflected. Okay, and actually, that is a key word. I should note that. You'll see that in some of the questions. If you see the word undeflected, okay, sorry, I kind of jammed that in there. That's a key word. That means that forces are balanced, okay? And that sets you up to do exactly what I'll show you here, and Thomson did this. You basically just say, well, if that's the case, then we can start with this expression right here. We can say that the force electric is equal to the force magnetic. Fe is equal to Q times E, or EQ, times the force magnetic on a moving charge would be Q times V times B. And as you saw there, the Q's cancel because they're on both sides. And Thomson didn't know what the charge was, so that was kind of nice. But then you can manipulate for the velocity. And sometimes I've seen this called it's called the velocity selector formula. Not that you really need to remember that title, but that's what it became known as, is because you could easily determine how fast the electron was moving if you knew the strength of the electric field and you knew the strength of the magnetic field. Okay, and those we can change. Like there's ways we can measure that pretty easily and with a lot of accuracy. And so Thomson was able to come up with that. So you may, on occasion, be asked to determine the velocity of an electron, but that's the setup. Now, the other one that was really cool was Thomson figured out that if he only turned on the magnetic field, that he would get circular motion. Okay, if you remember the electric field, maybe I should add this. The electric field, okay, the electric field causes parabolic motion. Okay, if you remember that from chapter 13, and a magnetic field causes circular motion. Okay, so they're similar, but circular is really interesting because if you make the chamber big enough, you can actually get it to do what this picture is showing right here. Okay, so I'll go back to the math in a second, but if you can just follow this, this is a cathode ray tube. I've got a heater here, and you accelerate the plates. There actually is a negative and a positive plate in here, but that's just so you can accurately determine the velocity. Okay, because if you know how fast it's going and then you let it go into only magnetic, so you can see all the red dots in here. Okay, all of those red dots are pointing out. Okay, so those are that's a magnetic field coming out. And if the let's see if the electron is, oh wait, I might have that backwards. That must be going into the, it must be going into the chamber, because the magnetic force on each of these charges, if you use your third hand rule, the magnetic force would be directed perpendicular like this. Okay, so sorry to keep moving that around. So the point is that Fm is going to cause circular motion. Okay, and what's awesome is, again, you can't see these electrons, but if you have these detectors, if you have a detector down here, okay, it can detect, I mean, you just kind of have this region, but you can detect where the electron strikes the this part of the cathode ray tube. And knowing that, you can actually work backwards and you could determine the radius r. Okay, let me clear that off. So you could find the radius, and that would be the radius of curvature. And with that, because so you got the velocity, you have the radius. You could know the strength of the magnetic field because you're imposing that over the actual chamber, and then you can say this. Okay, you can say that the force magnetic is causing centripetal force, and we've already done this already. If you remember in chapter, I guess it was chapter 12, with magnetic fields. This is exactly what Thomson was able to do. But as you can see, when you get down here, he couldn't go farther than this in his breakdown, because basically if he put all the variables that he knew, so he could determine the velocity, he knew the magnetic field strength because he was making that, and he could measure the radius. So he could get those three variables, but these two he did not know. He didn't know the charge on an electron, and he definitely didn't know its mass. I mean, this thing had to be ridiculously small, and it was. So he solved it to that point, and it became known as this. Sorry, it became known as the charge to mass ratio. Okay, so Q over M. Okay, so he was able to derive it. I know I'm jumping back and forth here. He was able to derive it right there, charge to mass ratio. And when he did that, he got this number. Okay, 1.76 times 10 to the 11th coulombs of charge per kilogram of mass. That is an insane amount of charge per kilogram of mass. It's like saying, okay, whatever these particles are, if you got a kilogram, a solid kilogram of whatever these particles are, it would have 1.76 times 10 to the 11th coulombs of charge. That's like 1.76 times 10 to the 11th lightning bolts, all contained in like a 1 kilogram mass. That's insane. The point is that they had a huge amount of charge per kilogram of their mass, which meant a number of things. One, it meant that their mass was extremely small. And two, it meant that they had a lot of charge. So you should be, and so if you see the charge to mass ratio, if you see a question with charge to mass ratio, this is the setup right here. Okay, you're only going to get that if you're just using the magnetic field, right? We're not using the electric field here to determine the charge to mass ratio. And anyway, Thomson he quickly realized after messing around with this that he could determine the mass of charged particles using this setup, and it became known as a mass spectrometer. You might see that in some of the questions, but a mass spectrometer is this is it. This device enables scientists to determine the charges on isotopes. So we'll learn about that in the next chapter, but you can have charged particles of different elements, and if you shoot, but they have to be charged, right? Otherwise, this isn't going to do anything, because a neutral particle is not affected by a magnetic field. So as long as it has a charge and you can shoot it into a magnetic field, it will bend into a circle, and using this device, you can determine the velocity and the radius, and therefore you can go backwards and you can solve for the mass. Now, in Thomson's case, though, he didn't know the charge or the mass, so he could only go that far. And it was left up to one of his students, actually not one of his students, but later on, a number of his students helped with our understanding of the structure of the atom. So this is what we end on with Thomson. His model was the plum pudding or the raisin bun model, and he basically confirmed that the electrons were individual particles. But the positive part of the atom was a bit of a mystery to Thomson because he couldn't confirm it with his apparatus. So he basically just said, hey, there has to be a positive blob or a positive mass, and then the electrons are embedded in it like raisins or plums. Right on his heels was this man, Robert Millikan. Robert Millikan designed an experiment to verify both the mass and the charge for the electron, and it was called the oil drop experiment. So I did post a video on that, but and it's really good. Essentially, it was just a chamber that had two plates in it, and the top plate was positive, the bottom plate was negative, and by placing a small hole in the top, Millikan sprayed oil droplets, like out of an atomizer, it's called, or like if you have maybe one of your grandparents has an old perfume bottle that you could spray with a bulb. Doing that actually charges the droplets a little bit, but to ensure that they got charged, Millikan fired X-rays into the chamber and hit these oil droplets to ensure that they were charged. So this part's happening right here. He's hitting it with X-rays. I always smile at this because it's like you got to make sure you're, because he's also trying to observe it, so you don't want the X-rays like going into your telescope. So he probably had them set up so they weren't, you know, going into his eye when he's trying to look at it. But anyway, so gravity itself will cause the droplets to fall, but with the plates being charged, some of the droplets would be just the right mass such that the electrostatic repulsion would cause them to levitate. Okay, so what you need to appreciate here is these droplets are coming. In fact, this graphic shows it. There's droplets coming in, and they're all of varying sizes. This kind of shows it up in here, and you know, Millikan came up with this really cool way of determining the mass of the droplets. He used hash marks that were scratched onto his viewing glass, and with those he could either take pictures or he could just only focus on the droplets that were not falling, that were actually levitating. So they were just staying perfectly still, and he could then measure the diameter of the droplets, and then he could do a calculation on their mass because he knew the density of oil that he was using. So anyway, it was really cool how he was able to figure out the mass of these droplets. What you're after though is, again, here's another key word. I talked about undeflected in the cathode ray tube. In here, the key word is suspended. Okay, if a drop is suspended, that's a huge clue, because that means that the force of gravity down is being balanced by the electrostatic force up. And Millikan knew that. That was his goal. He was like, I'm gonna set this up so that I can then do some math to determine the amount of charge on the oil droplet. So we had to get the mass of the oil droplet, but I already shared with you how he did that. And then the math here is actually really simple. Because if we say that the electrostatic force is equal to the force of gravity, then look at the cascade here. We can go Q times E. The electric field, of course, is the voltage across the plates, and then the distance between the plates. Okay, and Millikan was able to determine the mass of the oil droplet. So the mass of the oil droplet would go here. The voltage, of course, is there, and there's the distance between the plates. The acceleration due to gravity. He could solve for Q. Okay. Now the point is, he never did, like, it was almost impossible that each oil droplet would have just one electron on it. So they all had, multiples of a specific number of electrons. Okay, so they had, 10, 15, 20, 25, whatever. Okay, electrons, like, because he'd get these really small oil droplets. What he found, though, is that every single charge he calculated was a multiple of 1.6 times 10 to the negative 19. Okay, now there's actually a whole bunch of decimal places after that, but he just found that every single one was a multiple of this number. So by deduction, he was like, this must then be the charge on the electron, and he was totally right. So what was awesome about this, though, is now that, see, and I just showed this again right here, because Thomson had already come up with this charge to mass ratio. As soon as Millikan figured out the charge, he could just plunk it in here, and then he could figure out the mass. So he kind of got 2 for 1, okay? Because Thomson had already done the work to get the charge to mass ratio. So a huge contribution. By the way, everyone I'm showing here, they all won Nobel Prizes for their stuff. And what's cool about Thomson, I should back up to him, is he had a number of graduate students that were working under him, and 2 of them were Ernest Rutherford and Niels Bohr. So I think Thomson has the record for the greatest number of students who actually won Nobel Prizes in history. Like, anyway, they're a really incredible group of men that were working on these problems. So if you get an oil drop experiment, this is all you're seeing. Oh, I should add this one. On occasion, you'll get a question where you'll have an oil drop, but it isn't suspended, okay? And if it's not suspended, that means that the force of gravity down is not equal to the electrostatic force up. And in my example, I just showed you the electrostatic force is greater than the force of gravity down. So what it just means then is that you would have a net force, okay? So the net force would equal the electrostatic force here plus gravity, okay? So you've done these in Physics 20. The net force would expand to mass times a net, okay? The net acceleration, if you will. And in this case, that would be up. The electrostatic force would be Q times the electric field strength, whatever that is, and that would also be positive. And then, of course, gravity in this case would be a negative mg. Sorry about that. A negative mg. Okay, so in the course of us addressing a problem like this, if it's not suspended, remember again, slow down. If you see that word suspended, that should trigger your brain to saying, wait a minute, forces have to be balanced. If they're not balanced, no big deal. You actually have to address a net force problem. And I think there's a question like that in the review, okay? So obviously Millikan didn't really care about the droplets that were going up or down. All he cared about were ones that would just be balanced based on his strength of electric field and everything. So far, the model is still the same. Millikan just added to Thomson's raisin bun or plum pudding model. Now, one of Thomson's students, Ernest Rutherford, conducted a number of experiments using gold foil. So this is called a gold foil scattering experiment. I posted a really good video on that. I encourage you to watch that. It's actually really fascinating. And he did this, he confirmed, his big conclusion was that atoms have a very dense, positively charged nucleus, okay? How he confirmed that was firing alpha particles, okay? We're gonna start using alpha particles. The symbol for an alpha particle, whoops, let me try that again, is it's the symbol alpha, and we usually put 2+ after it, okay? So alpha particles, they're 2 protons and 2 neutrons, very stable. Rutherford basically put those, he had a radioactive sample and he stuck it in a lead cube, okay? So like you drill a hole, so the lead absorbs these alpha particles except for the ones that will leave the hole, okay? So then you're making a beam of alpha particles. You're just shooting them, in this case, at a very thin piece of gold foil, okay? And if the atom was structured like what Thomson thought, then the alpha particles should just fly right through, because there isn't a dense positively charged mass in the atom according to Thomson, and so these alpha particles wouldn't encounter anything densely positive, so they should just fly through. And that's basically Rutherford's idea, was like, this is how it should work. When Rutherford did it, though, he totally didn't happen. Well, actually, most of them did go through. If you see these arrows here, most of the alpha particles made it through no sweat. Like weren't even deflected at all. But some were deflected, and some of them were deflected in crazy angles. Like depending on, every so often, he'd get one that would bounce off at some wild angle like this. And the ones that just blew his mind, every so often there would be an alpha particle that would come in and hit it would be, I mean, it'd be hitting a gold nucleus, but they didn't understand that right at first. And then it would bounce back. Okay, so it literally came in and right back, like came back 180 degrees. And that was just mind blowing to Rutherford because they were not expecting that at all. So again, how the apparatus worked, you have this circular screen, like it's a phosphor screen. Remember, that's that same little trick. And they, I think some of his assistants had to sit in the dark for hours looking for flashes of light, indicating that alpha particles had struck the phosphor screen. And they just make note where they were and do the math backwards. But yeah, they noticed most of the alpha particles went straight through. So there was like a definite concentration of light flashes right behind the gold foil, but every so often they'd get a flash over here and over here and over here and over here and something like that. And they weren't expecting that at all. So this validated actually that the nucleus is very dense and it's at the center of the atom and it's positively charged. Okay, and that's actually where all the protons are located. I'll just mention this math. You don't see it very often, but it did pop up on a diploma question a while back. If you take these alpha particles and fire them at a gold nucleus, so what you need to realize here is a gold nucleus, I'll maybe just try and half sketch it here like a little raspberry. A gold nucleus would have 79 protons. Okay. Now it'd have a bunch of neutrons as well, but those wouldn't be a factor with electrostatic repulsion, if you will. Okay. And here, let me make this up. An alpha particle coming in is only 2 protons and 2 neutrons. Okay. So that alpha particle is really small. Initially, the alpha particle would have a whole bunch of kinetic energy, and Rutherford would have had a way to figure that out. But as it comes in and approaches especially if it hits it head on, so we're going to take that as our to keep our math simple. If the alpha particle comes in and hits this massive, now by comparison, okay, the gold nucleus is a monster compared to the alpha particle. Okay, it's 79 protons. This alpha particle is going to come in and it will only get so close to the to the gold nucleus before it comes to a stop. Okay, so initially way out here, right out here, it's got a whole bunch of kinetic energy, but by the time it gets to here, all of that energy has now become potential energy, and it's like elastic potential energy. It's like the alpha particle comes in and then it's slowed down, it's brought to a stop by all this repulsion from the gold nucleus, and then the alpha particle goes flying back. Okay, so it comes in, repulses, stop, and then it gets pushed back. So it experiences a change in energy. It basically converts all of its kinetic energy into potential energy, and then obviously from that point forward it just goes flying backwards. And the gold nucleus, basically, we're going to say for our purpose, it doesn't do anything. It just stays there. So this is the thought process behind how Rutherford deduced how big the nucleus actually was. So all he did was he realized that the change in energy here, the change in energy is going to equal the work done. In this case, well, you could say by the gold nucleus if you want, or whatever, which would equal the force that they both experience times the distance between them. Now the force is going to be the electrostatic force. Like this could be Q1 and this could be Q2. Okay, so we've done this, if you remember, with electrostatic charges. We just got a massive Q2, but the force that would exist between them would be, let me change colors here. It would be, KQ1, Q2 over R squared. Now I'm going to do this in blue. So this would be the distance R. Okay, now Thomson didn't know that number, but what he was able to deduce, though, is that if he substitutes in the electrostatic force, KQ1, Q2 over R squared, times the distance, then the distance that the force is working over, if this is kind of how I tried to rationalize it, the distance over which the force is working over is the same as the radius. So this this D and this R are exactly the same number, okay? It's this distance. It's the distance from center to center between the alpha particle and the gold nucleus. So that means that this D will cancel one of those R's, okay? And then you're left with, let me just clear it out. You're left with this, okay? The change in energy is equal to K Q1, Q2 over just D. And he knew the charges on both, and he could figure out the change in energy by measuring, if you can follow this, he could just measure the initial kinetic energy, EK. All right. Just knowing that, because there's basically 100% conversion from kinetic energy to potential, if that makes sense. Okay. So, whoops. So, this became his formula, and he was able to then measure D. Okay. The distance between or at least like when at the point that the alpha particle comes as close as it can to this that gold nucleus. Okay, so anyway, the conclusion was, and he did with his math, he basically got a number. I think it was 2.3 or whatever, but it's times 10 to the negative 14. Okay, now an atom, the diameter of an atom is times 10 to the negative 15. Okay, so it's a power of 10. Oh, wait, sorry. No, I did that backwards. I think it's a little smaller than that. Yeah, sorry. So the point is that the diameter of the nucleus is it can't be greater than this distance times 10 to the negative 14. Okay, so and that was much smaller than the diameter of the atom. Okay, so the conclusion was already mentioned, as I said before, that Rutherford made the conclusion that the nucleus is dense and it's positively charged. Will you ever have to do this math right here? Probably not, but I think there was a practice question where I threw it in. It's not something on your formula sheet, so it would be explained in terms of, I tried to do that too, but just to show you that it's not impossible. So Rutherford then came up with the planetary model, or that's the one I corrected at the beginning, with the nucleus at the center and the electrons orbiting it. Now, Rutherford immediately knew there was a problem with his model. Anytime you have electrons orbiting, or you have an object in orbit, it is experiencing a centripetal acceleration, okay? Because if you look at it in one plane, like the electrons here, and it's going back and forth, back and forth, back and forth like this, okay? So if you look at that on one plane, it's like it's doing what I'm trying to sketch for you right now. It's going back and forth, back and forth, back and forth. And that means that it is, if you have a charge and it's accelerating, it's going to emit electromagnetic radiation, okay? And that means it would lose energy. So Rutherford knew that right away, but he didn't have a way to explain it. So this little graphic here shows what would happen. So as the electron would start to orbit the nucleus, it would emit, you see this here, it's showing that it emits radiation. So it would lose energy and then basically just spiral in and crash into the nucleus, which doesn't happen, of course. Like, matter is stable. And so Rutherford's like, we got to fix this, but I don't have the means to do it right now. And it took, it was the setup for Niels Bohr, okay, to step in and provide an explanation. So Niels Bohr was another student of J.J. Thomson, which is really cool. And his model, if you remember, his model changed Rutherford's model to show that electrons only exist in stable energy levels. They can't exist anywhere away from the nucleus. There's only specific distances and positions where they can exist. And they he called them energy levels because they were a function of energy. So the summary is that Bohr used the science of spectroscopy. Okay, that's the study of visible light to explain his theory. And spectroscopy had already been established before Bohr, but no one had explained why they were observing specific colors in studying visible light from heated objects. So I'm going to attempt to summarize that right now. But I want you to just keep in your mind that this is going to confirm that electrons can only exist in discrete energy levels. So the three types of spectrums are, you need to know the difference between them. And if you take a hot glowing solid, okay, so sometimes I like to add that, a hot glowing solid, okay, so like a filament in a incandescent light bulb, if you happen to heat up some iron so it's like glowing red or whatever, a hot glowing solid will emit all of the colors of light, of visible light, okay, so Roy G. Biv. But when you look at a hot glowing object, you don't see all the colors. Like if you look at an incandescent light bulb, you basically just see white light. Okay, but that's because you're seeing all the colors at once. To sort them out, we can do two things. You can use a diffraction grating, which is what this graph does. And so then by diffraction, the colors will spread out. You can also do it using a prism. Okay, so I can maybe add that, or prism. Okay, because with a prism, you get refraction, okay, not diffraction, but you get refraction, and you would get the colors to spread out in reverse, okay, but you'd still see the same thing. So a prism or a diffraction grating will do this trick, and that's what a spectroscope is, by the way. A spectroscope uses either, most of them use diffraction gratings because those are pretty easy, but you could have a prism in there as well. All you got to do is get a piece of this light, so you can make a little slit and make the light shine, the white light in this case, shine through that, and then you would see all the colors, a continuous spectrum. To verify this, though, there's another way that you can create a spectrum, and that is to take a hot gas. Okay, so this is an excited gas, and you'll see that in, I'll show that in another one. So you get a hot gas, it's excited, it's energized, and then you shine that light through a diffraction grating. What happens is you get a whole bunch of black, you get a whole bunch of nothing, but you get very distinct colors and in certain locations. Okay, so you get a color here, 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 and so on. Okay, this is called an emission spectrum or a bright line spectrum. I've seen it called that too. Okay, bright line. Okay, and the other one, I'll just explain the other one. The other one is the cold, or the absorption spectrum. This one, you take white light, okay, or a hot glowing solid. You let that light shine through a cold gas, so an unexcited gas, okay, cool gas or unexcited gas. And then what happens is, because it is white light, you'd expect to see a continuous spectrum, and you kind of get that, but now you get one and it's missing colors. So it's missing a whole color right here, like some certain wavelengths are not even present. And that's because the photons that correspond to those wavelengths, those photons were absorbed by the cold gas. Now, worth mentioning here is that every element on the periodic table, starting with helium all the way up to, unobtainium. No, sorry, that's from Avatar. That's not on the sheet. All of the elements have a distinct spectrum, and you can identify it just like you can identify barcodes on products you buy at the store. It's so cool that you can shop the universe basically by identifying these distinct spectrums. Okay, now, sorry, 1, 2, and 3 there just describe what I already did, so you're welcome to review that. Here's again some bright line spectrums, and you can see they're different for every element. Hydrogen, sodium. If we were in class, I could show you some of these because I have some gas discharge tubes that we can use to actually view these. You can see them with a diffraction grating. Just hold up a diffraction grating to your eye and you can see them. They just spray on the back of your eyeball and you can see it. What's worth noting, of course, is that if you compare a bright line spectrum to a absorption spectrum for the same element, you could probably guess, well, it is noted, but this one is Mercury. This absorption, oh, it says it right there. This absorption spectrum is Mercury, because look, see these two line up with this, that lines up with this. Okay, so everything lines up, and you could confirm the element, right? But you either have an absorption or an emission spectrum. Okay, now that's just what the spectrums are. Now what the heck did Bohr do with that? So Bohr, what he realized to explain that is basically this, and I'll try and compress it here a bit for you. We can imagine an atom to be a nucleus. Okay, whoops, sorry. I'll maybe sketch it here and then just erase it. It'd be a nucleus, and then have electrons can exist in a number of different orbitals. Okay, so you could have only one electron, which hydrogen does, by the way, but that electron could be in this orbital, or it could be in this one, or it could be in this one, and so on. In fact, actually, hydrogen has 6 possible orbitals. And the first orbital is called they call that n equals 1. That's highlighted down here. I'll erase this and then we'll talk about it. This is the stable energy level. Okay, it's where the electron is most likely to be. It's where it's the most stable, so that's where it would tend to be most of the time. However, if it absorbs energy, so if a photon of light comes in and the electron absorbs that energy, it has to be the exact amount of energy. But if it's the exact amount, the electron can jump up to the next energy level, and it can be stable right there, and so it'll stay in that orbital. And or if the photon came in and it had even more energy and it was the exact amount, the electron could jump up to another energy level. That's called absorption. Okay, and that's what happens in an absorption spectrum. The photons come in, the electrons absorb that energy, and they jump up. So I'm going to actually, yeah, here, let me clear this out. And let me, oh, sorry. And then the point worth making is when you see an energy level diagram, which is what this is, okay, all these lines right here, you can imagine that the nucleus is down here. Okay, so when you see like different energy levels, an energy level diagram would look something like that. You can imagine, if it helps you, that the nucleus is right here and the electrons would exist here, 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 and here. But if you can imagine, they would, you're just looking at a piece of their potential orbitals, like the orbitals would they would wrap around the nucleus. Okay, so that helps you visualize this. I think it'll make more sense. Okay, so the electrons are normally in the stable energy level. From here, they can jump up to other stable energy levels. Okay, something like this. And there's a whole bunch of combinations, right? Because if you're an electron and you're in energy level number 2, you could jump up to number 5 or number 6 or whatever. Okay, so this is absorption. Or basically this would be a dark line spectrum would result from this. Okay, so absorption is when electrons jump up energy levels. When they're at an excited state, they won't stay there for very long because it's not necessarily as stable, but they're stable enough that they can be in that energy level. Then they'll fall back down to more stable energy levels. And that's what all of these arrows are over here and here. Okay, I'll just get rid of those. But that's, this would be emission. Okay, an emission spectrum. So when the electrons fall down, what you have to imagine is the electron, let's say we take, and I'm going to do this question, well, actually, let's just talk about it generally. Most of the time, see, when these jumps here, where the electrons are way up here and they fall all the way down, they release so much energy that it's not visible, that it's ultraviolet or X-rays. Okay, so you can't even see those. And then these guys here, those drops are so small that they're like infrared. Sorry, I got to be clear when I say this. When they drop down, they release a photon. Okay, they release a photon that has the amount of energy, or has the energy that equates to the energy level difference, the difference between this energy level and this one. Okay, so the energy that the electron had way up high, it loses that energy as a photon and on its way down to the stable energy level. So photons are leaving, okay, from an emission spectrum. With an absorption spectrum, photons are coming in, okay? So a photon that's carrying just the right amount of energy will excite the electron. Now, if the photon comes in and it doesn't have the right amount of energy, well, it'll just carry on. Like it'll go right through the atom because the electron won't absorb it. It'll only absorb photons. Electrons will only absorb photons that have the exact amount of energy that will let you jump between the energy levels. Okay, so here I'm just going to clear all this off. So what we look at, and this is the simple math, but it has complexity in terms of how to apply it. So the Bohr concluded that the specific colors of light correspond to the changes in energy that the electron experiences as it jumps up or drops down. And this is the equation. The change in energy is equal to the energy final minus the energy initial. When you're looking at an energy level diagram, this one's for hydrogen, I mentioned that. You'll notice that the energies are listed here. Okay, so each energy level has an amount of energy, but it's listed as a negative, and this is in electron volts. So this is negative 3.4 electron volts, and classically, an hydrogen atom in its most stable energy level has a negative 13.6. Now you might wonder why it says negative 13. Why are the numbers negative? Well, the point is if you're an electron in the stable energy level, you need an input. You need a positive 13.6 electron volts. You need a positive 13.6 electron volts. You have to absorb that much in order to completely leave the atom. To get so much energy, that you leave the atom, okay? And you would form an ion. So these are basically ionization energies at that level. See, if you're already in the second level, okay, you're an electron here, you're at an energy level of negative 3.4. So that means you only need a positive 3.4 electron volts, and then you're gone. Okay, like I'm already energized, but if you hit me with you hit me with a photon that has 3.4 electron volts, I'm out of here. That's enough energy for me to leave. Okay, it overcomes the positive attraction from the nucleus, and I'm gone. So that's why these numbers are negative. And you can see when you get way out here, like when you're in an electron and you're in energy level number 6, like you're right at the edge of the hydrogen atom now. You don't need very much energy because you're already energized in the first place. You only need a positive 0.38 electron volts, and you're gone. Like now we have a hydrogen ion, okay, because the electron left. So the math here, I'll just do one question here with you. You're going to see some in the review. Determine the energy and the wavelength of a photon emitted by an electron that drops from energy level number 3 to energy level number 2. Okay, now using hydrogen, we're just going to use these numbers. If you're, I'll just maybe do it right up here because you can see it. The change in energy that the electron experiences will be the final energy minus the initial. The negatives might trip you a little bit, but don't let that throw you off. The final energy, so if he was in the third energy level first, we're basically following this arrow right there. That's the arrow that shows the energy level drop. The final energy would be a negative 3.4 electron volts. And I would subtract from that the initial energy, which is a negative 1.5. So in this case, obviously, if I'm subtracting a negative, that's going to be positive, okay? And that's going to give me a negative 1.9 electron volts. And the negative should make sense. The electron would have lost, the delta E should be a negative because I'm losing energy. I'm going from level 3 to level 2. So I'm losing um, energy. And here, let me get rid of this. So that is that would take care of the energy of the photon. So see what happens is when this electron drops, a photon leaves. A photon is created. Okay, so I don't know. A photon sometimes drawn as like a kind of a jelly bean with a little squiggly in it. I just did a horrible job of trying to depict that. Um, oops, something like this. Okay, and then yeah, that's ugly. Anyway, so the photon leaves, but the photon would have this much energy. So to determine the wavelength, we can use the one expression for the energy of a photon that has wavelength in it. And then when I solve for that wavelength, I'd have to use the 4.14 times 10 to the negative 15 electron volts. And anyway, I get 6.54 times 10 to the negative 7 meters. Or actually, I like seeing it in nanometers, 654 nanometers. Okay. And if you look at your, you can see that. If you look at the visible spectrum, 654 nanometers is, it's in the red zone. Okay. So, yeah, this photon would be a red photon. It would be, and that would show up on an emission spectrum, okay, for hydrogen as a red. And you know what? And there it is right there. That would be the one red color that comes off of hydrogen if you heat it up and then let that light go through a diffraction grating. Okay, I know this one has it backwards. I like left to right works in my brain. This is right to left, whatever. Okay, so and there's the answers right there. Okay, so the last part then. Anyway, that's all you'd have to do with Bohr is deal with energy levels for the most part. Bohr's main limitation was he could only describe hydrogen. Okay, and there were a couple other things that he couldn't describe, and they're listed right here, and they're fairly specific. Why energy is quantized, and also why orbiting electrons do not radiate electromagnetic energy. Bohr was able to address that just with hydrogen, but he couldn't explain anything past that, which is what this one says. Bohr's model wasn't accurate for 2 or more electrons. And there's also this really weird phenomenon of the spectral lines having multiple, or the spectral lines being split in a magnetic field. You don't need to know that, but yeah, Peter Zeeman discovered that. It's known as the Zeeman effect, apparently. So the model required further refinement in order for it to kind of match what the heck was going on. Now, a number of physicists contribute to this. Peter Zeeman was one. Erwin Schrödinger kind of gets credit for coming up with a wave equation. It's a really fascinating equation. I've not studied it, but I've seen pictures of it. It looks very complex. But what he was able to describe was an electron existing as a wave. And what it looks like is basically, or the quantum model basically says that electrons act like waves. And as such, you can define where an electron would be stable if it would have a stable wave configuration. So that's what this graph shows. See here on this side with constructive interference, at a certain distance from the nucleus, if the electron's wavelength is, say, so here's a crest to another crest, okay? There's one wave right there. But if you determine what the electron's wavelength is, then if you can get a stable configuration, so this one has 1, 2, 3, 4, 5, basically it's got 5 wavelengths. Okay, so if you have 5 wavelengths, that's a whole number of wavelengths, and that means the electron would be stable at that distance. If you come in a little bit, then you can't fit 5 wavelengths in that configuration, and you get this happening. Okay, so like at a narrower distance, the 5 wavelengths don't fit. It's like cutting out, and I did this at the school. You cut out those, you cut out waves out of paper, and then you wrap them around themselves until you can get it to perfectly fit. And at the distances you can do that from the nucleus, that's where the electrons are stable. Everywhere else, they're not stable. Okay, they won't even be there. So anyway, Schrodinger kind of nailed this one on the head with his wave explanation. And of course, it built on de Broglie's model, which is that particles can have wave-like properties and electrons do. Okay, so this became the way to explain all the other elements, and it's how we understand them now, is that the electrons exist as stable wave configurations in the energy levels where you can find the electrons. So, the first energy level is basically made up of one wavelength. You can only get one wavelength of, as long as you can fit one wavelength around, this, around this diameter, around the circumference, I should say, not the diameter, the circumference. If you can fit the wavelength around the circumference, then that's where the electron will be stable. In the second energy level, you could get two wavelengths. You see that? Oh, whoops, I didn't do that right. Two wavelengths would be basically, here's the first wavelength would end here, and then there's the second one. Okay, so you can get two wavelengths. That would be like, here's one wavelength, and then here's two, or something like that. Okay, I'm not a great sketcher. And then here's three. So there's 1, 2, 3 wavelengths, and so on. So that pattern, like, that was the missing link, and it like clicked. So everything else made sense. But what else was really fascinating about, what is fascinating about the quantum model is that it's based on mathematical probabilities. We do not know with certainty where the electron would be. We only know where it's most likely to be. And if you take physics or chemistry in university, you're going to learn all of these. These are called shells, and they show where the electron is going to be around an atom. So this would be like energy level number 1, and or no, this would be like 1 electron. And if you have 2 electrons, then the electrons could exist here and here, or they could exist here and here, or here and here, and so on and so on. So you have to account for the three vectors, the X, Y, and Z plane. Anyway, you get some really cool configurations. Like this one here is like a little donut with 2 spheres. Anyway, it's really, really cool, but very complex. So you don't have to worry about those, though. What you need to know about the quantum model is summarized here. It's based on mathematical probabilities because of the nature of where the electrons are. It's sometimes called the electron cloud model, because you kind of have a cloud of probabilities. See, that's what all of these are. You have a cloud of probabilities that the electron's located somewhere in there, but nowhere else, and the other electron's somewhere in there and nowhere else, and so on and so on. So, expanding that model enables you to understand the nature of the atom. So, in summary, then, that was pretty long. Sorry, this video has been a bit long. I was just trying to grab it all in here. We have this progression in the structure of the atom, and it does note the weaknesses of each model as you go. There are a few math calculations, but definitely a lot of principles. With J.J. Thomson, there was a couple of formulas, including Robert Millikan's one. With Rutherford, you mostly just need to know the theory behind Rutherford, but there is a formula that if you happen to see it. And then Niels Bohr deals with the changes in energy as electrons either jump up orbitals or fall back down. Okay, so absorption if they're jumping up, emission of photons if they fall back down. And then the quantum model, all you need to know are the principles behind it. There's very complex math to define that. But that is chapter 15. So I'm hoping you can do the practice questions with that. And later I'll be posting a kind of a homework test on chapter 15. So anyway, keep up the good work, you guys.